Welcome to Breadboarding. In the previous video, we were looking at decoders and multiplexers, and this was an example of a 7-segment decoder. So originally we started with a 74LS47, and then we swapped it out for the 247, which has pretty much the same functionality apart from the 6 and 9 have the top and bottom segment that makes the digits look a little bit neater. Now we're just using this dip switch down the bottom, and we're just pushing the values up and down. So if we move that to 7 or down to 1, and when we look at 9 you can see that we've got the tail on the 9 as well there. So we'll perhaps make use of the 7-segment display a little bit later when we start to look at counters. So this is video 11 in the How to Use Breadboards and Retro Digital Electronics, and in this video we'll be looking at flip-flops and counters. So if you want to know detailed information about how all these sort of types of flip-flops work and how they're derived, then really the Ben Eater videos starting with the SR Latch and various other follow-on videos for flip-flops, I'd recommend you look at that video. I'm going to be covering some of this in summary and really focusing on the chip components rather than how to actually make one of these flip-flops in the first place. So flip-flops and latches are related, and the starting point really is what's known as the SR latch. So it's a very simple circuit. Basically 2 NOR gates is all we require, and generally when we're looking at these we talk about the positive output being Q and the inverted output being Q bar, and we have 2 inputs, the set and the reset, and that's the SR in the latch. And basically when we have the set goes high, then Q goes high and Q bar goes off. When reset goes high, then Q goes low and Q bar goes high. And if we had set and reset set at the same time, that's kind of an invalid state and it doesn't really define a particular output. And Ben goes into the details of then how a circuit like that can be extended to make these other types of flip-flops. So we're coming back to the D-type flip-flop and the JK flip-flop a little bit later, but I'm just going to look at the SR latch first of all. And if you remember from some of the earlier videos that we were looking at the NE555 timer, and in fact, if you remember this particular circuit, there's an element to this circuit which is in fact an SR latch. And in fact, this particular SR latch had an additional reset as well. But basically what the 555 timer did was take a voltage from the 2 comparators here, and at one level it would set the latch, and at the other level it would reset the latch. And it was a little different here in that we had the Q bar here and the Q output here was just on the other end of an inverter. But this was basically the logic table that we had from the earlier videos. So when reset is 1, Q goes to 0, when set is 1, Q goes to 1, and when we have 1 and 1 then it's in an invalid state. And in fact, because of the way how the comparators work, then you wouldn't ever get a situation where we had 1 and 1 in this particular case. So let's take a look at a breadboard with the simple circuit. So this is a simple SR latch, so basically just using 2 NOR gates here. If I zoom in we can see a little bit clearer. You can see I've got 2 NOR gates. The output of this lower one is connected to one of the inputs of that one, and the output of this one is connected to one of the inputs below. You can see that the blue lead is the reset and the red lead is the set, and I've got Q is green and Q bar is yellow there. So if we switch this on, the initial state is kind of not really determined, it just depends on which gate comes on more quickly. So if we do the set first, and because TTL inputs, when they don't have anything connected to them, they default to high or 5 volts. And in fact, the green LED comes on actually before we even tie this to 5 volts. And then if we put this off, then the green LED still stays illuminated. Then if we do the reset, you can see now the green LED comes off and the yellow one comes on. If we then go back to 0 again, the state stays the same. And obviously as soon as we unplug that, we get set. And if we do both, then in fact we get neither of the LEDs, and this is our indeterminate state. So it's a very simple gate, but a lot of these other circuits are actually based on this particular type of latch. So the D-type flip-flop is probably the most common used in retro microcomputers. Certainly the vast majority of flip-flops that you'll see in the IBM PC designs are D-type flip-flops. There are a few of the JK ones, but there aren't many. So the D-type flip-flop has two outputs, Q and Q bar, a bit like we had with our SR latch, and we have the data input and a clock. And generally the clock will latch the value on the rising edge. So as it goes from low to high, generally it will latch whatever the D value is to Q and Q bar. So this acts like a very simple single bit of storage, so it can be used for things like registers, but also quite often what you'll see with the D-type flip-flop, that the Q bar output will actually be fed into the D input. And what that means is when this first switches on, then the Q may be 0, but Q bar will be 1. And on the first input clock pulse, that means that that 1 will feed into D, and then it will be propagated to Q. Q bar will then go to 0, and then on the next clock, then the output will then toggle to 0. So it toggles between 1 and 0, and that's really where the term flip-flop comes from. So if you have a clock input here, say this is a 10 Hertz input clock here, then this coming out will be 5 Hertz. And what we'll be looking at is dividers and counters will make use of this type of divide by 2 operation. Now, one of the other things to note is as we look at some of the different chips which are used for flip-flops, some will have a preset and clear. So in a bit like the SR latch had a set and a reset, then in fact the set is active low on this 74LS74, which is one of the most common D-type flip-flops, and reset is also low. Now the JK flip-flop, the name came from around the 1950s, I think, as some papers and books were published by a particular author, and I think because of the different categorization of the different types of latches and flip-flops, JK stuck with this particular one. And in fact with the JK flip-flop, the J sets the output, the K resets the output. But unlike this SR latch, when we have both the set and reset, or the J and the K set, so when the J and K are both high, then it will toggle the output. So that means that when Q is 1 and Q bar is 0, when we get the J and K high, when the clock comes in, then the 1 here will change to a 0, and the 0 here will change to a 1. And if we then get another clock signal, then they will toggle back again. So that really is defined behavior for this particular condition that was causing problems with the original SR latch. So before we play with the D-type flip-flop, I thought I'd just show you a couple of schematics from earlier projects, and just to show how prevalent flip-flops are and how complicated the circuits using them can be. So this is a schematic out of the original PCXT. The monochrome display adapter was the text-based video controller. And we can see here I've highlighted in orange all of those chips on here which are the flip-flops. So the 174 contains multiple flip-flop gates, the 74 contains 2 each, and then there's even a JK flip-flop here, the 112. So we've got in total there 17 flip-flops. Then the CGA display adapter, color graphics adapter. This again has some of these 174 chips which contain, I think, about 6 gates each. We've also got another JK flip-flop there, another D-type flip-flop down the bottom here and here, and then we also have a counter here which is actually used for dividing the vertical sync frequency to provide the character blink and cursor blink clocks. Then finally, this is one I'm currently working on at the moment. So the Compact Despro 386, I'm looking at doing a breadboard version of the 386, and this is considerably more complicated. And you can see from this reset, DMA and refresh logic, there's a lot of flip-flops here. We've got combinations of the 74175 on this particular schematic. And also we've got both the ALS and the fast Schottky devices as well. So the F series is higher power requirement than the LS and the ALS, but has actually got gate times of a couple of nanoseconds, which are needed in some cases where the timing is particularly sensitive. So let's take a look at the most basic D-type flip-flops. That's the 74LS74. So just have a quick look at the datasheet first. You can see that we've got two flip-flops, 1 and 2, and we've got the D input, the clock input, Q and Q bar output, and then we've got a clear, which is active low, and a preset, which is active low. So clear will 0 Q, preset will set Q to 1. And if we look at the function table down here, we can see that in fact the preset and clear will affect the output no matter what the clock signal is. So as soon as we put either preset or clear to be low, then the Q output will change immediately. It's not dependent on the clock signal here. Whereas when both preset and clear are high, then only when we have the rising clock signal will the D input get reflected on the Q output and the inverse of that on the Q bar. So let's look at a simple test circuit for our D-type flip-flop. So I've resurrected the 555 timer circuit. So if we just switch this on to start with, you'll see that the LED down here is blinking very slowly. So I've changed the values on here. I increased the capacitor there from 1 microfarad to about 4.7, and the 220 ohm resistor here has now been changed to be a 500k variable resistor with about a 10k resistor, so we don't go too fast. And so you can see now this is turned about as slow as it will go, and if we turn it up, you can see we can change the speed, and see about there it's flashing probably almost too fast for the camera to pick up. Okay, so we'll crank this all the way down to about once every 3 seconds. Now if we have a look at this circuit up here, we'll just zoom in. So what I've got is a green LED on the Q, yellow is on the Q bar. I've got these two black wires are currently connected to 5 volts, are for the clear and the preset. And then at the moment I have the D input is connected to 0 volts, and there is that LED will show when that is on 1. So if we just try out the preset first of all, so we have the Q bar is on and the Q is off. So if we now just do the preset, we can now see that Q is on and Q bar is off. And if we do the clear, and you can see that has cleared it. Now if we now hook up the clock signal to clock, you'll see there won't be any difference if we just zoom out so you can see the clock signal. So if I change the input D to be on, you can see that it doesn't change until the clock goes high. And again, if I now change the input D to be off, it only changes again when the clock signal changes. So what I'm just going to do now is to try out the circuit that we looked at a minute ago. The D-type flip-flop, when configured to divide by 2, then in fact the Q bar output is fed into the D input. And so if we have a clock input coming in here, then the output here will be half the frequency. So if you just connect that up, I'll just unplug this, unplug the input there for the D, and we'll now connect Q bar now connected Q bar to D. Now when we switch that on, what we would expect is that the green LED will flash at half the frequency of that, and obviously they will alternate between the two when this one flashes. So you can see it's flashing at half the frequency. It's a little difficult to see when it's this slow, so let's just speed it up a bit. You can see here that the output is flashing at about half the frequency. Now, the reason why that's useful is because we can use that for dividers and counters, and that's what we're going to go on to in a minute to have a look at. Now, I was going to look at the JK flip-flop. I have actually ordered a JK flip-flop. The only one I have at the moment is one that has a K input is active low, which makes it a bit awkward to do tests with. So I'll do the JK flip-flop perhaps in the next video once the parts have arrived. So it's just worth looking at the data sheet for the D-type flip-flop again. So this is the function table we looked at earlier. And there's also a logic diagram here. So you can see here that the gate design here is very similar to the SR latch that we looked at the beginning. However, this is using NAND gates, and it's using 3-input NAND gates in this particular case. And in fact, the original SR latch with NOR gates, we could actually produce the same circuit with NAND gates. However, the set and the preset would be active low rather than active high. But you can see here that the preset and the clear and the clock and the D are actually feeding into very similar sort of gate combinations anyway. And we certainly wouldn't want to be making our flip-flops using this type of circuit, which is why we use these chips. So we've been looking at the 74LS74, which is a dual D-type positive edge-triggered flip-flop. And you can see that in addition to the clock, the D input, the Q and the Q bar output, we have individual presets and clear on each of the flip-flops, and each of the clocks is also independent. Now, the one that I've still got on order, I do have a 109 of these, which is very similar, apart from the K input actually is inverted. So in order to play around with that, we'd have to put an inverter on the K input. So I'll wait until the next video to deal with the JK flip-flop. And there's two other chips that tend to get used quite a bit in the PC in particular. So the 174 hex D-type flip-flop. So you can see here that all these 6 flip-flops here all have the same common clock. And I'll explain why that's an issue a little bit later. And we can see that we've got a D input and a Q output, so we don't have the inverted Q output. Now that means that we can't easily produce a toggle using this particular circuit because we need the inverted Q output to be able to feed back to D. And you can also see we don't have any preset, but we do have a common clear. So we can actually clear all these to 0 and we can clock them in common. So this circuit can be used for latching data. So in particular in the XI8088, then the port B on the XI8088 would use this type of flip-flop to latch the outgoing data for port B. And you can see this one's very similar, the 175, but this is a quadruple D type, and the difference with this is that on the outputs we have both the Q and the Q bar, so it would be possible to actually tie the Q bar to the D input. However, because again we have common clock here, so the clock is shared between all 4 flip-flops and the clear is shared between all flip-flops, then there are certain things that we can't do. And one of those is if we wanted to actually make a counter. This is the diagram for a ripple counter, and if you remember the first slide I showed that we connect the Q bar output back into D, and that will result in dividing this clock signal divided by 2, so this will be clock divided by 2. We then feed that into the next clock input, and similarly feed back there, then the output of that into here and the output of that into here. Then in fact we can take out of the Q outputs the 0, 1, 2 and 3 bits out of there. Now in order to do this we'd actually need 2 74LS flip-flops, so that's a bit cumbersome to wire all these up, so there's actually chips that actually do this for us. So these types of flip-flops are useful for certain things, so certainly if we're needing to clock things together. So sometimes these are used in state machines and they're used for calculating cycles and things, for example, in the video cards for doing some of the dot clock level timing. And this 273 flip-flop, in fact, as I know, is used in the Compact Despro 386 as part of the bus control state machine, for example. And the key thing really that this has is having the common clear as well as the common clock is useful in that particular case. Counters actually avoid us having to do all this, and in fact the 74LS92 is a divide by 12 counter. There is also, I think, the 9091 of variations of binary counters, divide by 16. The divide by 12 is sometimes used, I think this was used in the nanocomp originally, for dividing down one of the crystal frequencies to provide the baud rate or the serial port, for example. And if you look at this diagram here, it should actually look quite familiar in that this is using, rather than D-type flip-flops, it's using JK flip-flops. This is in fact wired up very similarly to the diagram I've just shown you in KiCad, and in fact there's a separate clock A here, and in fact if we want this to do a divide by 12, then in fact we feed the output of QA into clock B, and then in fact we've actually got pretty much the same circuit that we had before. So what I'm going to do is to wire this up, feed the 555 timer input into clock A and then also into clock B, and we're going to take the output here. I'm going to try and feed that into the LED 7-segment display that I showed at the beginning, and we'll see whether or not we can get that to clock upwards. And we'll also see when we go past 9 that obviously display will give us the different characters we saw last time, and I think on 15 it's actually blank altogether. So we're just going to go and have a look at that on the breadboard and wire that up. Okay, so I've wired this up now. So we've got our 7-segment decoder here that takes an input A, B, C and D. So I've put in the blue, green, yellow, orange wires, which are sort of similar to the ribbon cable colours we use. And we've got our timer down the bottom here. So this is producing our clock with the flashing LED there, and this is going into clock A. Let me just zoom in so we can see the pins there a bit clearer. So the clock's coming into clock A, and then QA is then also feeding into clock B as well. And over on this side, these sort of enables. When these are both tied to 5 volts, then it disables the counting. And if either one of them is 0, then in fact it will allow the counting to continue. So basically when both of those are high, then it stops and zeros the counter. Now we're just going to turn this on, and we would expect to see sort of digits increasing over here, and when we get above 9 then we'd expect to see sort of various symbols on the display until it resets back to 0. Now this is a divide by 12 counter, so this includes logic to 0 things after 12 or 13. So you see at the moment we've got 0 here, but that's because the counting is inhibited here. And you can see that we're flashing at probably twice a second there. So I'm just going to tie one of these inputs to ground, and that should enable the counting. There we go, 1, 2, 3, 4, 5, 6, 7, 8. One of the things you'll notice here, it actually kind of skips. So it is actually a divide by 12 counter, but it isn't actually producing the exact sequence of digits. So if we were using this for dividing a pulse, for example, we would actually get a pulse coming out of here, which would be 12 times slower than the input clock, but it isn't actually counting exactly the way how we would want it to be able to display incrementally going up on this display here. So what I'm going to do now is to have a look at another counter, and one that hopefully will do what we would like, which is to count sequentially from 0 up to 9. So the reason why we saw strange outputs there was because this is a divide by 12 counter, and it does include some logic to handle that. But this next counter we're dealing with is one that we've actually used in some of the video controllers. This was used to take the dot clock and to produce the necessary timing signals for providing the character clock and also other various attribute latch type signals. And the reason why this is called a synchronous counter is that because of the logic on all of the JK inputs here, the clock is actually shared between all of the flip-flops here. So because the clock is synchronous in this particular case, then it reduces some of the interference and things we can get. You can get spikes and things from ripple counters, So synchronous counters are generally the sort of thing we would want to use in more complicated circuits to eliminate any of that interference. So if I swap out the LS92 part for this one, there's a few other things we need to worry about here. It is possible for it to preset the inputs here. So the A, B, C, D inputs will allow the preset for the load pin there. We have the clock there, we also have the clear, and there is actually a ripple carry out. So if we wanted to, we could tie multiple of these counters together. So I'm just going to go and wire up, and hopefully when we look at that, we'll be able to see that it will count from 0 to 9 properly. This is a circuit wired up. This is a 74LS163 synchronous binary counter. It's capable of counting from 0 up to 15. We just zoom in to have a look at the pins and what's connected to what. So we have our +5 volts and ground. Then we have two enables. Now at the moment, both the enables, ET and EP, are both connected to 5 volts, which means they're enabled. We have a clear, which I've currently got tied to 5 volts. There's a load as well, which is currently tied to 5 volts. We'll look at those when we start playing around with the circuit. We've got QA, B, C and D are connected over to our decoder, so we can see the output on the 7-segment display. That will show everything from 0 to 9, and then we'll get some strange characters from 10 up to 15 with being blank. Now these are the preset inputs. Now these only actually do anything when we tie load to 0 volts, but what I've done here is I've enabled DA to be 1 and all the others to be 0. So this will mean that it will preset this counter to 1, and I'll explain why we need that in a few minutes. And then we've got the output from our 555 timer oscillator here is going into the clock signal there. Let's just zoom back out and turn it on. You'll see that it started to count. You can see that the oscillator here is fairly slow. It's 7, 8, 9. Then we get the strange characters for the higher values. We'll go blank for 15. Then goes back to 0 again. Now, if you want to, we can clear that. So if we do the clear it to 0. Start counting again. Now, if we try the load, we'll just make sure we get past 1 to start with. So past 1, now if we do load, it'll give us 1, and it needs at least 1 clock pulse, and then after that, it will start counting up again. So if we increase the speed, we can get to a situation where we can probably do it a little bit faster, but that's now going pretty fast. Now, what I was thinking is we could make this into a digital dice. Now, what we need to do is to get it to, rather than resetting to 0, we want it to be set to 1 when it gets to 6. So what that means is we need a 0 output to load when both QB and QC are 1. And now that would mean that we'd actually want a NAND gate there. So if we just wire up a NAND gate, so the two inputs need to be QB, which is green, and QC, which is yellow. And then we're going to plug the load from 5 volts to go to the output here. So we'll just turn the speed back down again, turn it on. So it starts at 0, 2, 3, 5, 6, and it goes back to 1 again. This looks like it's actually giving us what we would need for a dice, apart from the first run through it will do 0 on the very first cycle, but after that it will actually go through here. So if we just speed up this, and what we can do is just disconnect the clock, and we get a value. Four, 5, 2, 6, 6, 1, 1, 4. So relatively random. I guess we could actually put some sort of logic analyzer on there and actually see exactly how random those signals are, but it's not a very practical dice since we actually need to run it off a 5-volt supply, and it's not exactly portable, but at least it shows that we've been able to get the 555 timer producing a fairly fast oscillator signal, using the synchronous counter then to then send the outputs to our 7-segment decoder over here through this resistor array into our 7-segment display, and then we've used the gate here, so the NAND gate here will actually set the load to be 0 when we get to 6, and so when the next clock pulse occurs after 6, it'll actually load 1 in there and then start counting again. Just crank the speed down again. So I've now seen two types of counter. The ripple counter isn't really something we'd want to use in most circumstances, certainly for higher clock circuits, just because of the interference that can come from the ripple counter. But the synchronous counters are really used in quite a number of places within the various designs I've been working on over the last couple of years. So in the next video, we'll be looking at buffers, latches, and shift registers. On the buffers, we'll be looking at how to clean up some of the output when we shove high-frequency signals down bus rails, just to see if there's anything we can do to improve that. So as you can see, we've managed to get the oscillator hooked into our counter and then driving our 7-segment decoder to actually drive a display. So we've got something that passes for a fairly simple dice. Really, we'd want to probably speed up the clock hit somewhat and give ourselves a push button, and perhaps have some sort of slowdown in the clock as it approaches the value, but certainly seems to be showing values between 1 and 6. We would probably want to do some sort of analysis of this to make sure that things were truly random coming out of this before we used it for anything, but it's been a useful exercise just to bring a number of the steps that we've done over the last couple of videos together. If you don't want to miss out on future videos, please hit subscribe, and if you found the content interesting, please hit like, it just helps to make it available to more people. Thanks for watching.